how do you think this unit went?
I think it went really well.
Yeah.
Like, I was pleased with the student engagement and also their learning, and like how they're able to think about gases versus how they maybe would in a traditional gas laws unit.
Talk more about that.
Well, I think that a lot of times when students are in a high school chemistry class, they might just learn quickly. Maybe the teacher might tell them pressure and volume are related this way. Here's a gas law. Temperature affects it this way. Maybe show them an animation, but I don't think they have as much time to think and really experience those relationships as, or in that kind of unit as they did in this one, where they were really investigating those relationships and having to think deeply about what could be causing some of those different things to happen.
So say a little bit more about how you structured the unit so that it wasn't just a walk through the different gas laws.
They started out with that problem about the tanker, and they had to try to figure out why it would crush. And through that, they kind of started to think about different ways that gases behave, and then they worked on their pop can investigations. The first one where they just crushed it, and then the second one where they had to investigate their own idea about what might be causing the can to crush. And even though some of those got pretty complicated, I think it really made them think about their variable that they were testing, like what could different temperatures or what could different volumes, how did that affect the behavior of the gas in the can? And so I think they really started to think about what is pressure, what is volume, what is temperature, more than they might if I had just said P1 V1 equals P2 V2.
And then, so following those experiences, you sort of allowed them to get these questions in their mind and sort of made it complicated, but then you broke it down.
Then we looked at just relationships between pressure and volume. Or first of all, what is pressure? What is the balance of pressure? And then just what is the relationship between pressure and volume? What is the relationship between pressure and temperature? And some of those were a little more traditional ways of doing the math, kind of the math problems about it. But I think that I got the feeling that it wasn't just a math problem, like they could actually think about what is pressure, what is volume in this problem.
What sort of helped you have that feeling?
Well, like on one of the worksheets that they did when we kind of got to the traditional pressure volume, and they had pushed down their syringe and they measured the force, and they could see that as the volume got smaller, the pressure got higher. Then I also asked them to draw like a syringe and explain why the pressure would be getting more, and they were drawing molecules in there and like explaining it instead of just saying because V goes down, P is going to go up. Like they weren't just saying the rule, they were also looking at it at the molecular level.
So part of that was that you'd shown them this way of this representation for thinking about molecules and thinking about the tanker and in the can too, and then they were able to apply not only the concepts but that type of representation too.
Yeah.
I think, and then you didn't stop there.
Oh yeah. So then after we looked at all those relationships, and we kind of looked at all the relationships you could have with gases, like the P and V and the P and T and B, then I wanted them to kind of apply that to another situation, and so they did the engine. They learned about how the 4-stroke engine works, and they had to look at each stroke of the engine and think about what's changing here. Is number of molecules changing? Is pressure changing? Volume or temperature? And then, like, for their final thing, they got to see how they would modify their engine by adding turbochargers and things like that, which I think continued to force them to think about, well, what is this doing? What are these relationships, and how do they work in like a real life application? So, yeah.
Great. So one of the things that I'd like to do is sort of think back to the beginning and trace some of the kids' lines of reasoning throughout the unit. And so it seems like after they had done after they had drawn their initial tankers, we saw some initial ideas emerging, some that seemed interesting, some that seemed right on, and particularly like ways that they were applying the kinetic molecular theory from the previous unit. And then, but then also we noticed that there were some ideas around pressure that they were struggling with. And so if you could talk about both of those lines of reasoning, their kinetic molecular theory and pressure, and sort of how you saw that unfold over the whole unit.
Okay. So starting with pressure, we noticed in the beginning most people didn't mention pressure at all as a reason that that tanker might crush or the can might crush. I think maybe one group said something about pressure differences, but mostly they were thinking of it as like, well, a lot of them I think just thought it was magic. But they talked a little bit about phase changes and things like that, but they weren't really explaining what would cause that. And a lot of them didn't talk about any air pressure or atmospheric pressure around the tanker or the can at the starting.
So the external
pressure. And as time went on, I saw most students starting to add those air molecules outside around to signify atmospheric pressure.
But that was in part a conscious choice on your behalf. Like you saw that they were sort of missing that part, and then you added that part to
Yeah, we talked about it as a group. Like they read about atmospheric pressure from a textbook and had to try to draw what that would look like. And so I think that helped most kids start adding that to their picture and thinking about air pressure. And then we continued to think about that balance of pressure, because even when they got through their can crush, a lot of them still were having a hard time saying what would cause crushing. And this balance of pressure, like, being the cause. And so then we did that, the stations where they looked at the marshmallow and the balloons and just kind of really had to say, this pressure is more than this pressure, and what is causing each pressure. And so I think that helped them describe how a pressure difference or change could cause crushing or expansion.
So you were purposefully giving them just a little bit more information about pressure to reason with and add to their existing models.
And I think for most of them, like at the end, that the idea of pressure, they kind of all realized this is the most important thing. It's like this balance of pressure. And so that was a major change from the unit, like from day one to day whatever. Like, I think any student would say one of the big ideas here is there's pressure being caused. But I think one thing I noticed was that some students still weren't able to say like what was causing that pressure. So like they might say there's pressure outside, but they're not saying it's because there's air molecules outside causing pressure, or there's pressure that's decreasing inside, but they weren't linking it to that understanding of the kinetic molecular theory.
So let's talk a little bit more about kinetic molecular theory and how you saw that sort of get woven into this unit
I think
in
that,
their minds.
I think that they came into this unit knowing a lot about that. We had done the unit on phase changes and phases of matter. And they had, I think, because they had acted it out, I think I've told you before, like they had to act like a solid, they had to act like a liquid. They really knew that the different phases had these different kinds of movements. And they knew about temperature making molecules move more quickly. And which is interesting because sometimes they know that, but oftentimes it's not clear in their, like I think the idea of temperature and heat and movement of molecules isn't always clear. But they do know that temperature would make the molecules move more quickly. So they came into that already. And so I think when we started the can or the tanker, even on the day one, some were showing or talking about molecules moving more quickly if it was heated up or slowing down if it was cooling down, and able to talk about that. And
then some were able, during the can, some of the kids were able to also talk about the phase change as it begins to cool down.
Yeah. So I think they brought a lot of that phase change and movement of molecules in. And then what I was hoping for them to do is really start to make that link between I'm getting more collisions against this can or fewer collisions against this can, so I will have less pressure.
Some of them really did work with that. And then you saw that in the final assessment, too, that a lot of kids were thinking about the collisions that are happening, at least inside of the can.
Yeah, they definitely were explaining, like, as I heat up this can or cool it down, how do the collisions inside the can change? And then
and linking that
it to pressure. Some kids did a really good job of like explicitly linking it to pressure. Some kind of stated this happens and pressure, like molecules slow down and pressure decreases, but it wasn't always clear that those were linked. Like so, I'm not sure.
Make the causal link.
Yeah, and so I feel like if they were saying something about they slowed down and so there were fewer collisions, which made less pressure, then that was a pretty good causal explanation. But if they just stated it separately, I wasn't sure if they knew that that was linked or if it was just these were both happening at the same time.
And they were able to talk about both those ideas with phase change too. So how did they do that? How did they talk about the molecules, the phase change, and pressure?
Yeah, if they were able to say like along the lines of we had steam in a can, like the water vapor molecules, and they were making collisions, and then they turned to water liquid molecules, and so then there would be fewer collisions on the can. I think that would be good reasoning of why the phase change would also cause a decrease in pressure inside the can. And I wouldn't say that in their writing, I'm not sure that all kids, well, a lot of kids didn't say that. But it seemed like when we would talk about it verbally, they could, like if I tried to push them to go to the next step and then what happened, they could make that connection.
So it sounds like what you're saying is that you saw a lot of partial understandings. I mean, this is a pretty complex set of chain of events to explain. Or that they had each piece, but it was the linking of them that they're still sort of struggling with. But it sounds like the big leap was this idea of pressure, and actually some of the kids were able throughout the unit to at least label pressure, label that, because it seems like in the beginning they weren't even sure what it was.
Yeah, they weren't really mentioning it at all.
But at least then they had a term to describe what they had seen happen.
Yeah.
And then some of the kids were able to link pressure with the change in the molecular movement.
And then I would say like maybe some stumbling blocks or kind of partial understandings that got in their way of understanding, of being able to like fully explain it was one, like what is air, what is gas, and so we'd try to be explaining we have this water and it's heating up and it's turning into water as a gas form, but a lot of times that would be there's also air in the can, and then trying to explain which one of those was undergoing a phase change and why that would matter, I think was a stumbling block for a lot of kids, and I tried to help them draw that by using different like X's and O's for the different types of molecules, but I think it was still a little bit confusing, especially since gas or air, like we use the word air and gas often interchangeably, so I think that would be something that if I could help them be more clear in the words that I use and that they use to describe what was happening, it might make their understanding either show through more or show through less. I'm not sure, but yeah.
So that a lot of the kids were not necessarily thinking about which gases were involved, but just sort of saying
this gas that's in the can.
Which makes sense because it's difficult to even interpret that there's multiple types of gases in the air that we breathe. So but you think that would help afford a different kind of reasoning?
I think it would help them explain the part about like the phase why the phase change, explain the phase change clearly and how that would make pressure inside the can decrease. Because it's those water ones that we originally evaporated and now they're condensing, and because there's fewer molecules now of gas in the can.
Of which gas?
Of the water, exactly. So total gas molecules have decreased, and it's because the water gas has decreased that then there are fewer collisions, and I think that would help.
It seemed like they bumped up to that against that when they were working with their car engines too, because some of them, and then you had the tricky thing about that it was actually gas, vapor gas, too. But it seemed like some of them had a hard time thinking about that, and that's what led you to do that warm-up question that day about what gases,
like
what gases are we talking about here?
And I got a lot of blank stares
Uh-huh.
because I think that is the trickiest part, because we can't see gas, and that's the whole point of almost the whole unit, is to like describe the gas that we can't see. And so
I think you're right to focus on it, though, because one of the cautions is, I think, that I've seen before, is that kids will attribute the gas laws to things like liquids or other molecules, and so it really is important to differentiate. This is the particular gas that we're, and the behavior that we're talking about.
Yeah.
So you think working with ideas and unpacking what we mean by air and what we mean by a gas.
Yeah, I think I would definitely add that to this unit if I were to teach it again.
And then you noticed, we'll talk about that in a minute. So then you did this great application with car engines and car tires, and it, again, complicated situation where the kids had to reason with all the different parts of the gas laws, the pressure, the temperature, the volume, the number of molecules. What did you see happen in that? Were they able to then apply a lot of what they had learned? And
yeah,
how
I think
did you see
that we watched that animation of the engine, and they could, if they were just looking at one part, I think they did a pretty good job of trying to say, well, I know the number of molecules isn't changing, because now they looked to see if like the valve was closed or open, which a lot of them we related back to the pop can. So the pop can's open, so we know that like air could go in or out, and the pressure was equal inside and outside, and so they thought about that when they were doing their engine. But I think that those relationships in the engine were complicated, but they had, I think some students were able to like really, they were able to ask each other, like, well, does this matter? Like, because what if, I know that if pressure goes up and the volume's going down but the temperature's going up, like, which one outweighs which one? Or if the valve is open, does that matter? And so I think that there are conversations where we're using parts of all the things that they had learned throughout the unit, even though it was complicated and it's not just easy to explain.
And did you see any ways in which they were struggling to make some connections? Were some connections easier than others for them during that engine?
Yeah, I think that, like, when we had done the pressure stations with balloons and expanding, I think that, like, the idea of those molecules making something, like, speeding up and making more collisions so that it expands, I think they really latched onto that. And I think that the compression part, they could relate to the syringe, so I think both of those, they could relate back to those previous activities. And I guess like the idea of the open system versus closed, like when those valves were open or not open, same with the pop can, I noticed that as like kind of a struggle for a lot of students. Why would that have an effect? So I think that was a struggle.
Okay. And I noticed that in those groups, that you were really good about when you would go to a group connecting back to, you've seen this before in this other experiment, but you noticed that students were doing that too. That they were able to go back and reference a previous experiment to help them explain some part of it.
I would hear students say like, oh, it's like the balloon, or it's like the marshmallow, or something like that.
Great. And then talk a little bit about how you think this experience with the engines provided relevance for the kids.
Yeah, it was really fun to see that a lot of students who maybe don't usually like chemistry or love chemistry were really excited about this project, and I think because they had a lot of knowledge, they just thought this was, kids would say things like, chemistry is cool or awesome now, or like this is when it gets fun. And then I think a lot of the kids who said things like that were the ones who, like, in their group, when they would go to learn about engines within their lab group, those kids were kind of the experts in their group. So I think that was part of the reason they thought it was so fun, is because they could really be the one in their group to say why you might want a supercharger, or just like even know what the thing was. Whereas some kids didn't know about that, and so it gave almost every group had a kid who maybe normally wouldn't be the one that the rest of the group would look to.
I noticed something else too, though. I mean, I noticed that about some of the kids. I think one who didn't typically participate, who came into your classroom one day and said, "Oh, Miss Schoberg, what are we doing today?"
Yeah.
When he saw the big, the Honda Civic on the board. But I also heard some of the kids say, "Schoberg, we don't know anything about cars."
Yeah.
And I remember you saying, "That's okay. I'm just learning about these too." And I think that sort of added a certain comfort, because then when I saw them in the groups, their avenue in wasn't the cars, but they knew these relationships so well, and these topics so well about pressure and volume. That was so strong for them that was their avenue in.
So there's different ways to
Yeah, I think there were different
work
kinds
together
of
as a group.
different kinds of engagement, and that really worked nicely together. And a lot of the kids, it seemed to me like they knew that you would need
intercooler to go with the supercharger.
Right, to go with the supercharger, or the nitric oxide button. They knew
They've
that,
seen it in movies.
Right, they knew that was important, but they didn't know why it was.
Yeah.
And it seemed like towards the end they could all tell you why those were important in terms of
the engine.
And use the gases to reason through that. So let's talk a little bit about this analysis. What's this final product that you have?
Okay, so at the end of the unit, we did a quiz, and part of their quiz was just some traditional calculations using gas laws, but most of it was more free response. And the problem I looked at for looking at the student work is the last one, where I drew out 4 steps of a can crushing, of the can crushing experiment. So I drew in the molecules like we had done as a class, and with the air molecules outside and the water molecules in the can and air molecules in the can, and then asked them to explain what was happening in each picture. So to tell kind of the story. So, and I gave them the same checklist on their quiz that we had used before. So it should have been pretty familiar. And that kind of what prompted me to ask this question. We talked about that when we had as a class gone through it, if we were talking about it as a class, we could kind of come to a consensus as a class the story, but we couldn't tell if each student could tell the story on their own.
Right.
And so that's what they had to do on their quiz for the pop can instead of the tanker, which we had already talked about as a class.
It looks like a lot of kids gave pretty rich responses.
Yeah, they wrote. I was amazed at how seriously they took this.
Yeah.
Like, that's one thing I thought about in relation to how much I felt like they learned in the unit. Because a lot of times I'll hand out a quiz in any class, and they'll kind of blow through it and write maybe a sentence to an answer. But for every question, both the question about the raft and then the whole pop can, every student, even some of the ones that are typically don't write much, wrote a lot.
Wow.
So I think they felt like they knew a lot.
Nice.
And some were able to express that knowledge, I think, better than others, and also some of their kind of partial understandings came through on this.
So let's talk about those.
Okay, so what I was looking for in their illustration, I kind of broke it down into you want me to say the 3 levels?
Sure.
So, like, I thought a level 1 would be something where the student would explain what's happening to the molecules, or they might talk about pressure, but they wouldn't really talk about both. So kind of just initial, to me that was still more, like it would show learning because it would be more than what they would have done during the first explanation.
Nice.
And then for level 2, I thought that they could talk about the molecules, like they should be describing the action of the molecules and maybe how they would change with temperature. And then they would also state that pressure balance was what was causing the crushing. So if one pressure was more than the other, you would get the crushing. But what I thought was that level 2 would not have a clear connection between the two. So like they might say the molecules are moving more because the temperature went up, or the molecules are moving less because the temperature went down, or the phase changed. But they wouldn't say which caused the pressure to be less.
Right. So the good partial Y.
And then the like level 3 would be really weaving those all together, like saying, I got the molecules did this, which caused the pressure to do this because, and like explain about collisions on the sides of the can. And also, to get it like a really full level 3, they should be explaining the molecules outside the can, causing the pressure outside the can. So I found that I kind of had students in all 3 of those levels.
So what were some of the other patterns that you saw overall?
Overall, I think most students, almost every student, said something about pressure change. Like I think that they really latched onto that idea that it's pressure that's causing the can to crush. Like if one pressure is more than the other, that will cause crushing. So I think out of these 9 students that I picked,
And that's a big shift, because my guess is if we'd asked them what's the number one thing that's causing the can to crush on the first day, they
probably
would've-
phase changes.
Yeah.
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 Because they almost all mentioned phase changes on that day 1. One student said no pressure is involved in crushing on the paper, which I was kind of surprised at. But I'm not sure if that's exactly what he meant. So he meant, because he also said there's not really pressure outside on one can, and on another can he said, the next picture he said the pressure, now there's pressure. So I think he was just confused. I might even be able to find that one. But every other student said something about pressure in their explanation out of these 9 that I picked. So I think that was the biggest increase, or the biggest, yeah, it's this one. So he said, the pressure inside the can caused the can to implode like that. So here he's saying, actually, he did say the pressure. So every student did say that pressure caused it. But then, like, in the next can, it says pressure is not really involved here. Or in the first one, it says something like, there's also a lot of pressure inside the can. So he does talk about pressure. So every student talked about pressure.
Which is not the external pressure.
And so that was a pattern that it seemed like every student did that. And then
Good learning outcome.
a lot of students were kind of in that level too. Like they said, they talked about molecules. They still were using their ideas of the movement of molecules. And they were also talking about pressure, but they weren't linking them together. And so I think that was the biggest pattern that emerged through the whole class. That, in fact, even the highest level students who kind of stated that pressure, they still didn't ever explicitly say, like, the molecules outside the can are what are causing that pressure outside the can, the air molecules. So
But they did talk about the relationship
between the pressure outside and the pressure inside, and the idea that the pressure outside wasn't changing. So they kept talking about the pressure outside, and I'm not sure if they just thought it was obvious that that's what was causing pressure outside because it's in the picture. But they did talk about, and because the picture was the same for each 4, but they did talk about how the molecules inside, how their behavior changed, and the collisions changed, and the pressure changed.
So we're at least linking those together.
Yeah. Let's see if there was any other pattern. I think also, so those were the 2 main.
Mai Nguyen, can you please come to the front office? Mai Nguyen, can you please come to the front office?
Those were the 2 main patterns I think that I saw. And then I had some kind of ideas emerge in their writing that I hadn't noticed before, like the idea of heat molecules, like kind of that heat was a particle, or that like the heat molecules or the cold molecules of the water were causing the temperature to change inside. And so it was kind of hard to tell from the writing if they mean just like the water's cold, or if they meant like there's actually like a molecule that's coldness. So so that was an interesting one that came out of reading their writing here. And I had a few students some of the lower students from this never mentioned any collisions. So they talked about kind of the lower half of the sample would talk about the molecules, but they weren't saying anything about pressure or even that there were collisions with the can. So I think you could say that there was collisions and not know that that was pressure, but just also not even saying that there were collisions, I think.
So the students who said this about sort of this particle theory of heat, how many students were that did that?
I had two
and was it
out of the sample, so 2 out of...
And was it typically the level 1 students, or would you see this sort of pop up?
I just saw it kind of pop up, so I put it, like most of their rest of their response would be like a level 2, maybe a level 2 minus, like.
So it really was sort of an underlying idea that you think. Where do you think that came from?
I don't know. Like this one said, as the can touched the cold water, the hot molecules inside the can reacted with the cold molecules, which I think he might mean that it's just cold, and the molecules that are water molecules outside are cold, and the molecules that are inside that are either water vapor or air, like, were hot. But and that kind of goes with that whole idea of what is this gas inside the can, like what's it made of.
Nice.
So I think that might be connected.
Also, the idea of like reacted is interesting there.
Yeah.
Because that's not something that I would have used to describe
and that
it.
was used by a few students. 2 of these students that I have talked about reaction, like still we're talking about that reaction between hot and cold, which was an idea that a lot of them had kind of at the beginning, that it must be some sort of reaction, and that was, I think, still.
Oh, okay. So you think it was an idea they entered into the unit with, and then it just sort of never got dispelled for them.
And so it kind of stuck with them that there's some sort of reaction happening, and that it's because we have hot versus cold.
I wonder how much of that is going to get cleared up in your next unit, because you are going into chemical reactions.
It was coming up next, yeah.
And so it could just be that they didn't know that they were misusing that term.
Yeah.
Or maybe I wonder what they meant by reactive.
Yeah, it's hard to tell from the context of their writing.
Interesting. Well, at least that's one you can continue to track too, and probably this idea around heat too in your next unit on chemical reactions too. So, anything else that you want to talk about, or just sort of what ways that you might think about adapting this unit again in the future, or what you've learned through this whole process of working with us? And
I would definitely teach this unit again like this, with the same kinds of lessons, because I think students really did learn a lot, and like we were just talking about, just the amount that they wrote, and especially like when they tried to describe what was happening to their raft on the river on a cold day and on a hot day. They had all sorts of ideas about why. I mean, most of them had a really good explanation of why that was happening, why it would deflate, and then they had all sorts of creative ideas about how they would make it not happen. And so I think it was just, they were really able to think about the gas in all sorts of relationships in the gas. And so I think that that is like the best thing about how this unit played out. And I think if I were to do it again, which I would think I'm teaching this next year, so I would just make sure I'm really focusing on clearly talking about what's in the gas, maybe even have them use, instead of just drawing like bubbles, draw the actual molecule, because then they have to say this one has 3 atoms, so it's water, versus it'd be hard to do with air, so since it's such a mixture though. So I'd have to think about that. And then let's see what else. I can't remember what else we just talked about that I thought was really important to do again. I think I would also have maybe another time as a class devoted to like this idea of open system versus closed system. I think that was important, and a lot of kids figured out that was important, but I don't think we ever like came up with that as talked about it as a class, that why that was important. So I think I would add that. But for the most part, I liked this idea of having them tell the whole story themselves, because I think it really showed what they were missing, and I think I maybe would do that earlier in the unit, like kind of as a formative assessment to see like where are they, like at what earlier in the unit I could jump in and kind of help them clear up a few of those confusions.
And it's great too that you were able to see them apply it to a totally different situation that they'd never even discussed before.
Yeah. So that was fun, except for the 1 or 2 students who didn't know what a raft was. I felt terrible. So next time I would have to like show a picture, because once I described it, they knew what it was. But anyway,
wow.
Yeah.
Wow.
So off the top of my head, that's what I would change, and I just feel like having this opportunity to really think about how students would learn gas laws has been valuable, because it really made me think about like what are all the parts that go into it, like why does pressure and temperature and volume, and how are they all related, and I think that the students were really able to kind of tell the bigger story of gas relationships based on me thinking about it first instead of just talking about random gas laws here and there.
Yeah. And that now they can use those different relationships or different ideas about pressure and temperature and which ones are key in different situations. That they have the tools to now reason with new situations.
And I agree. I hope it sets them up to really start thinking about chemical reactions, like how do those work? Why is it important that we know what a gas is and how these molecules might interact with one another? So, yeah.
Yeah. Great. Thank you very much.
You're welcome.